we've already seen that in some natural phenomena, quantities grow at a rate that's proportional to the size of that quantity. In this section, we will dig a little deeper into such models. So suppose we have a population of 100 bacteria that is growing at a rate of 20 per hour at a certain time. So it means if we start with 100 bacteria, we're going to have 120 bacteria after an hour. And that gives us the rate of growth. If we call that size of the population y, the rate of growth is 20 at that moment. Now, if we had a second population of 100 bacteria, that one would also grow at the same rate, and that would have a rate of growth of 20. But if we look at these two populations combined together, and that means we had started with a population that had a culture that had 200 bacteria to start with, and ended up with 240 after an hour, and that gives us a rate of change of 40 now. So if we kind of follow that reasoning, this implies that in this case, the rate of growth is always proportional to the population we had start with. In other words, dy over dt is equal to some constant k multiplied by the size of that population. And depending on the sign of k, this population either grows in this case, or it could shrink, it could decay. And we refer to this as the natural law of growth or decay, once again, based on the sign of the constant k. The equation we just saw, dy over dt is equal to ky, is what we refer to as a differential equation. It's an equation where you have a derivative on one side. And if we think about possible functions that could satisfy such an equation where the derivative is equals a constant times the value of the function to start with, it can be proven that the exponential equations in general would be the only possible ways that can be done. So we have a theorem that says the only solutions of the differential equation dy over dt equals ky are exponential functions of the form y of t equals y of 0, or the initial size, multiplied by e to the kt, where k again is the constant that gives us the relative growth rate or per capita growth rate of the population. Okay, so let's look at an example. Here we have a conservation group made up of biologists, and they're trying to preserve an endangered species of bats living on an island. They start their efforts in 2012, and at that point they count 2,930 bats living on the island. And in 2018, after they've done some interventions, they find that there are now 3,405 bats living on the island. Assuming the growth rate's proportional to the population size, we want to predict how many bats will live on the island in 2024. Right, so we'll start putting the information into in the mathematical notation to start with. We'll let 2012 be t equals 0, and that implies that y of 0 is 2,930. And we know in 2018, 6 years later, there were 3,405 bats, so that's y of 6. And we are asked to find the value after 12 years in 2024, right? So y of 6 is 3,405, and y of 12 we're trying to find. Now, we just saw a theorem that says as long as the growth rate is proportional to the population size, we're going to have an exponential equation. So we have y of t equals y of 0 e to the kt. And that equation we happen to know y of 0 for. So y of 0 is 2,930. So the equation turns into y of t equals 2,930 e to the kt. Right? So now there are a few things I got to find before I can find y of 12. And we need to find out what k is. So what's the growth rate of this population? So using the fact that y of 6 is 3,405, we know that if we plug 6 for our t, the answer should equal 3,405, right? So 2,930 e to the k times 6 is 3,405. That's the equation we're going to solve. So divide both sides by 2,930. We get e to the 6k equals 3,405 over 2,930. Take the natural log of both sides and then divide by 6, right? When we take the natural log of both sides, e to the 6k just turns into 6k, and then we'll divide by 6 to find what k is. So k would be 1/6 of natural log of 3,405 over 2,930, and that is approximately 0.02504, right? So the growth rate per capita at that time is roughly 2.5%. Okay, so next thing we're going to do is go and try to find y of 12, right? So y of 12 means we're going to plug in 12 into the equation that we have now established, which would be y of t equals 2,930 e to the 0.02504 times t. So plugging in 12, we get 2,930 e to the 0.02504 times 12, and that's approximately 3,957 bats. Okay, so let's look at one more example. In this case, we're looking at radioactive decay. We're told the half-life of carbon-14 is 5,730 years. So if you're not familiar with what it means to have a half-life, that means after 5,730 years, the amount of carbon-14 that's present is going to decay to be half as much. And then if I wait another 5,730 years, that half now becomes another half. So in this case, we start with a sample of 30 milligrams of carbon-14, and we're asked to first figure out how much of that 30 milligrams is going to be left after 2,000 years, and then how long does it take for that whole sample to be reduced to 20 milligrams. So again, here's a case where the growth, in this case the decay rate, is proportional to the size of the sample we have. So we go back to the equation we had seen already. So y of t is y of 0 e to the kt, and we know the initial amount of carbon-14 times 0 was 30 milligrams, so y of t is 30 e to the kt. Right, so this case, to start finding the k, the constant, we'll use the fact that we know the half-life is 5,730. That means y of 5,730 is going to be 15. After 5,730 years, the 30 milligrams will decay to be 15 milligrams. So using that information, this is the equation I need to now solve. 30 multiplied by e to the k times 5,730 equals 15. We'll solve it again by dividing both sides with 30. And 15 over 30 is 1/2. Taking the natural log of both sides, and then dividing both sides by 5,730. So that will give us that k is natural log of 0.5 or 1/2 divided by 5,730, and that is approximately equal to negative 0.000121. And the negative implies that the size of this sample is decreasing as we expect it to. Right, so this gives us the ability to complete our equation we started with. So we had y of t equals 30 e to the kt, and now we know what k is. So this equation is going to turn into y of t equals 30 e to the negative 0.000121 t. And now we can figure out the size of the population after 2,000 years by plugging 2,000 for our t. And that 30 e to the negative 0.000121 times 2,000 is approximately 24 milligrams, the nearest milligram. All right, so it answers part A of this question. Part B is asking us how long does it take for the sample to be reduced to 20 milligrams. So in this case, we know the value after t, we just don't know what t is. So the equation's gonna look like this: 20 equals 30 e to the negative 0.000121 t. And we'll solve it similar to how we solved the equation above. Divide both sides by 30 to isolate e, and then take the natural log of both sides to eliminate e from the left side. And then divide by the coefficient of t. So we'll end up with t equals natural log of 2 over 3 divided by negative 0.000212. 2 over 3 is 20 over 30 reduced. And the result of that using a calculator is approximately 1,913 years.